This is Calc 2, Lecture 2, Applications of Integration, and that's in fact Chapter 6 of the textbook, Area Between Curves. Well, let's first take a look at the Riemann sum. Riemann sum is behind integration. When you want to integrate, you write a Riemann sum and let say delta n go to 0 or n go to infinity, and then the limit of that, if it exists, is integral. That's the Riemann integral. But what we are finding, in fact, is area. So a definite integral is area of something. In this case, it is area beneath this curve, the graph of fx and the x-axis. So this is, in fact, this integral is this area. Now, to find area or any integral, one way is just write the Riemann sum and find the limit and do it that way. But another way is what usually they do in physics. They write down a differential of what they want to find, that is a tiny, minor piece of that, and then integrate that tiny, minor piece over the region that they want to find that quantity. Now, this is in fact area, but anyway, so what is the differential of area here? Well, you already know the differential of area, but let's look at it more carefully. So, at point x on the x-axis between a and b, we just go forward by dx. So this dx is very small, that's infinitesimal, so that's very small. Then if I go up like this, I will find a rectangle. In fact, you might say, okay, no, this is curve. But since dx is so small, we can assume that that curve is really like a line, say. Now this tiny, minor area, look, this dx is tiny, so this is a tiny, minor area. So that is what we call a dA, or the differential of area. What is the area of this differential of area, this dA? Well, I draw the picture here. So one side of this rectangle is dx, the other side is fx, so the area is in fact fx times dx. Therefore, this area, which is in fact integral of the differential of area, will be integral of this fx dx. Then I look at the variable here. The variable is x, so this integral is on x. Then I look at the these two, and so this is from a to b. Okay. Now this will become well handy in like when I discuss work, for example. For area, it's just easier to look at it the way that you already have in chapter 5 of the book. That's simply fx dx. So, but anyway, we see that it is, and in fact, if you ever take physics at some maybe higher level, you will see that physics professors, they prefer this method. I mean, they always write this. They don't write a Riemann sum. Okay. Now this section is very simple. It is in fact, it's saying, okay, now what if I have two curves? So let me draw the picture for you, and it's easy to see why the formula is like this. So here I have two curves. This one is for fx, say, and this one is like, say, gx. If I do the same thing here, if at point x I go forward by dx, then differential of this area, as you can see, is simply the dA is simply at point x, it is fx. This is fx, right? This is fx from here to here, fx, and this is dx. Okay, so that is in fact fx minus dx times dx, right? So this area, this is fx minus gx, and this is dx. So area between the two curves will be from, say, A to B again, if it's A, B, and that is fx minus gx dx. One can say it is the top one minus the lower one, or the outside one minus the inside one dx. Well, we will see that the terminology outside and inside will become, I mean, we have to use that when it comes to solid of revolution and volumes, in fact. So, that is if I have two curves given in this format. So, this is in fact y equals something, and this is when x is the independent variable and y is the dependent variable. Well, we can have these two just reversed. So well, we can have this. Now let me erase this picture and give you the formula. Now, well, let me give you an example so you see what I'm talking about. Say this is a y equals square root of x, right? So this is in the form y equals fx. And it's a one-to-one function when x is bigger than 0. So no problem. Now I can find x in terms of y. I cannot do that if the function is not one-to-one. But even if it's not one-to-one, we can just find x in terms of y, but we will get different functions for that. So it doesn't have one answer. So this one is one-to-one, so we can solve for x. If I solve for x, I will get x is a y squared. So this one is in the form of x is like a function of y. Okay? So well, since I use g for that, let me use, say, h here, some function of y. So if I have this format, if I am given two functions or two curves in this form, then the formula is almost the same. So in this situation, we have a picture like this. So I have this and this, say, and let's say it goes from C to D, and this is a graph of, say, x equals hy, and this one is say hk ky, say. And you can guess, if I go up to point y, then up by dy, then this element of, or this differential of area, the differential of area in this situation is in fact hy minus ky times dy. Okay, so that is differential of area, and it looks like this. That's dy, and this is hy minus ky. So the area will be, since it's unknown y, it goes from C to D, C, D, and I have hy minus ky dy. Depending on the situation, when you look at a problem, you have to decide which way you should go. Is it using y as free variable or independent variable or x as independent variable. Sometimes you cannot do it the other way, because then you cannot, in fact, invert the function. But if you can invert that, then you have to decide which one is better to do. So let me give you some examples here. Well, let's see, does the book have any nice example? Okay. So this is in fact quite nice. So let's say the one is sine and the other one is cosine. So let's find the area between the curves or the graphs of sine and cosine. Area between the graphs of sine x and cosine x from 0 to pi over 2. Well, you can use any graphing. You can use your graphing calculator to find it. So let's say this is pi over 2 and sine and cosine. So this is point 1. So this one is sine x, graph of sine x. And this one is a graph of cosine x. And this is 0 and pi over 2. An area that I'm looking for to find is this area. Okay. First of all, since y, we are given y equals f of x. So the problem is the problem that you should use the x-axis, in fact, the first formula. As I said, sometimes it's better to use y, for example, as the free variable. Now, in this case, we take x to be the free variable or the independent variable, and now, from 0 to some point here, from 0 to some point, cosine x is on top. So from 0 to some point, so area will be integral. From 0 to some point, which I don't know what that is, I have cosine x on top. Cosine x minus sine x dx. And from this point to pi over 2, which let's find it, then I will write it here, sine is on top. So it will be sine x minus cosine x dx. So depending on the situation, it's not always, when I said between these two, it's not always this one minus the other one. No, you have to graph it and see for yourself which one is on top on that interval. So if I went from 0 to say 4 pi, then sometimes this one is up, down, up, down, up, down. So I have to be careful which one is above the other one. Okay, let's find this unknown. So that's the point of intersection of sine and cosine. So when this happens a lot in problems like this, you have to find point of intersection of graphs. So how do you find point of intersection? Let me erase this and find the point of intersection. So you have to know some trigonometry. So I have, when you find intersection, it means the y coordinates are the same, right? The y coordinates are the same. So this should equal to this. So if you set them equal, you will find the x at which the y's are the same. So you set this equal sine x equal cosine x and solve for x. And I need an x between 0 and pi over 2, okay? So I just find one of them. Okay, now there are different ways to solve this problem, but the easiest way is this. Since cosine at this point is not 0, we can see that, so I can divide by cosine, so I have sine x divided by cosine x is 1. So that gives me tangent of x is 1, and referring to the trig, well, you can use a calculator or a trig table. You will see that x is in fact pi over 4. X is not just pi over 4, but since I'm between 0 and pi over 2, I just need the 1 between 0 and pi over 2. So it is pi over 4. That gives me pi over 4 as the limit of this integral, and also this one. Okay, so when the two curves intersect, you have to solve a simple equation. If it is trig equation, then you have to do this, something like this, and you have to, well, just take a look at your trig book or the pre-calc book or whatever you have, and anyway, so let's find this integral. Let's calculate. So let me erase this thing. I have enough space here. So the first one will be cosine x. The antiderivative of cosine is sine, in fact, so I have sine x. Antiderivative of sine is minus cosine, so that is in fact plus cosine x from 0 to pi over 4 plus. Sine x, antiderivative of sine x is minus cosine x. Antiderivative of cosine is sine x, so I have minus sine x, and that is from, what was that, pi over 2 to, no, pi over 4 to pi over 2. Okay. So, pi over 4 will give me a square root of 2 over 2, square root of 2 over 2. So I have, well, let me erase this. And be careful, 0, I have seen students, when they say 0, they say, okay, 0, 0. No. Plug in 0, maybe one of them is not 0. And that is in fact a good example. So this one will be sine pi over 4 plus cosine pi over 4 minus sine 0 minus cosine 0. So that's the first one. Plus minus cosine pi over 2 minus sine pi over 2 minus minus the pi over 4 minus cosine pi over 4 minus sine pi over 4. Okay. And my suggestion is write them explicitly on some scratch paper and then do the calculation. I mean, so this one is square root of 2 over 2 plus square root of 2 over 2 minus 0 minus 1 plus minus 1, there is a minus 1 here, minus, sorry, this is 0, but this is minus 1, and minus square root of 2 over 2 minus square root of 2 over 2. Okay, so this one is just square root of 2, that one is square root of 2, and I have plus, so this will give me 2, square root of 2. I have a plus 1 here, and minus 1, is that minus 1? So that is 2 square root of 2. And let me double check, there should be minus 2 somewhere. I might have made some mistake somewhere. Oh, let's see. Oh. That's plus. So minus 1, that's minus 2. Okay. So, yeah, I wrote minus here, but that's plus. Okay, so that is 2 square root of 2 minus 2. And again, I say, I have seen students immediately when they see 0, they write 0, 0. If you write 0, 0 here, then this will be wrong. You will get the wrong answer. So be careful. That 0 does not always give you 0. Not every function at 0 is 0. Okay. So that was area between sine and cosine, and that was in fact a very good example. Now let's do another one which we can do it either way. So example 2. This one is area between, say, so area between area enclosed, area of region enclosed in partial by area of region enclosed by the graphs of square root of x and x squared in the first quadrant. Well, you might say, well, if you continue these two, there's nothing else. But in order not to make you confused, because I have some students asking which quadrant, so I emphasize that it is in fact what I'm talking about is in first quadrant. Okay, so nothing else is given to us. The problem doesn't say that it goes from 0 to something, which we see that it goes from 0 to something. So we have to find the intersection point, this point. You can guess that this is 1, in fact. Well, let's find it. So we have to find this intersection point. And finding the intersection point is simply setting them equal to each other. And if I look here at the square root of x, x should be positive. So I can raise them to power 2. I will get x equals x to power 4. And that gives me x4 minus x is 0. And that's x4. X times x3 minus 1 is 0, and x is 0, and x3 minus 1 is 0, and this one will give me x is 1. In fact, it gives me two more answers which are complex, but I need the real answer, so these two curves intersect at 0 and 1. Well, you could see that they intersect at 0, but the solution, in fact, I mean, solving that equation, in fact, confirms that they intersect at 0. Okay, so let's do it using the x-axis, using x as independent variable. So if I use x as independent variable, I have integral from 0 to 1. Okay, the top one is this, square root of x, and the bottom one is x squared, square root of x minus x squared dx. So that is in fact integral 0 to 1, x to the power 1/2 minus x squared dx. And so that is 1 over 1 plus 1/2 x1 plus 1/2 plus minus 1 over 1 plus 2 x1 plus 2 from 0 to 1. So this is 2/3 x 3/2 minus 1/3 x3 0. 2/3 x 3/2, and for 1 this is 2/3 minus 1/3, that's 1/3, and for 0 it's 0. So the answer is 1/3. So that was using x as independent variable. Okay, now let's use y as independent variable. Right? So let me give some time so you can look at the solution. And be careful, I have some students and even Calc 4 cannot simplify this. Okay? So that's just, I don't know, like pre-algebra. Now, using y as independent variable, I have to solve for x and y. So this one is y equals square root of x gives me x equals y squared. So this top one is y squared. Now this one, if I write y equals x squared, if I write y equals x squared, you might say, okay, x squared is not 1 to 1. No, it's not. But in this interval, over this interval, it is 1 to 1. So if the interval of integration is such that the functions or one of them is 1 to 1 over that interval, then you can invert that function. So the inversion is x equals square root of y. Well, you might say, gee, this looks like the other one. Yeah, true. That looks like the other one. So this is square root of y. Okay. Now the integral again goes from 0 to 1. 0, 1. And the right side minus the left side, right minus left. So the right one is square root of y minus y squared minus y squared dy. But this integral is the same as the other one, except the variable is y. So I will get one touch. Okay, so that was an example that you can do both ways. There is another example which is a very nice and standard example that one of them works very well, but the other one doesn't really work well. So let me okay, another example is this. So let me write down, find the area enclosed by the line, area enclosed by the line y equals x minus 1, and the parabola y squared is 2x plus 6. And as you see, the y equals x minus 1 is okay, because you can you have x as the free variable and y is independent and then dependent variable. The other one, if you say x is the independent variable, then y has two answers for every x. So what we can do is this. We can say, okay, since this can be solved for x, and that also solved for x, so we can say that it is, in fact, x. If I solve for x, I will get y plus 1. If I solve for x here, x will be 1/2 times y squared minus 6. Okay, so I have these two, and I have to find the intersection of these two curves. Let me first graph them. The graph of these two is like this, so that y equals x minus 1. The x intercept is 1, x is 1, and the y-intercept is minus 1. So it goes through these 2 points. The other one is a parabola like this, 2x plus 6. I can find intercept. So if x is 0, y is plus minus square root of 6, right? So square root of 6 is bigger than 1, so it goes through some point here and here, say. And let me see, is that so, and if y is 0, x is minus 1, minus 3. So it was here, minus 3. So this looks like this, something like this. intersect somewhere, and this way come back. So this is -1, 1, and this is -3, and these two are square root of 6, and the down here is minus square root of 6, but I don't need this one, so yeah, so I don't need these two, but that's okay. Now I need these two intersection points, the one here and here, and since I'm using y, so I need the y coordinate of these two. So I need this coordinate and this coordinate, and so let's see, if I want to find those two, at these 2 points, the x's are the same, right? The x's are the same, so I want to find the y coordinates, so let's set them equal. So if I set them equal, I have y plus 1 equals 1/2 times y squared minus 6. And then I have y squared minus 6 equals 2y plus 2. So I have y squared minus 2y minus 8 is 0. So that is y minus 10. So y minus, say, 4 times 2, so that's 4, y plus 2. Right, so that is, so y will be 4 and -2. So this point is -2 and this point is 4. Well, I don't need the x's, but I will probably find the x's because I want to write down the integral using x. Okay, so I have the 2 points and I have these two, so this one is in fact y plus 1 and this one is 1/2 y squared minus 6. Right? So the area will be from -2 to 4, this one, y plus 1, which is the right side, minus the left side, minus 1/2 times y squared minus 6 dy. Okay, so let's simplify before we do anything. Inside this I have a minus 1/2 y squared, and I have a plus y. I have 1 plus 3, so I have a plus 1 here and a plus 3 here, so I have plus 1. Right. And always simplify before integrating. Some students just do not simplify and they integrate both of them, not realizing that this integral of this is something, okay, but this is also something, then they subtract. So you can do the subtraction or addition inside, so you can simplify the integrand before doing anything. So let me double check, so there's a 1 here and a plus 3 here, so that's 4. Okay, so I have minus 1/6 y3 plus 1/2 y squared plus 4y from -2 to 4. Well, I have the answer here, so I will waste your time. So the answer is 18. Yeah, 18. So in the end, you get 18. Okay, so as you see, the integral here is a simple one. We are using the y as the independent variable. Now, let me see what I can do. If somebody says no, let's use x as independent variable. So let me erase this and try to use x as independent variable. So I have y equals x minus 1 and the other one was y squared is 2x plus 6. But this one is okay, but this one is, well, I have to find y in terms of x, so I have y is plus minus square root of 2x plus 6, but which one is plus and which one is minus? So let me erase everything here. And because I'm just using need these points, this point, and this point. Well, I will find them. And no, the plus one is in fact this, the top one. The top one is y equals 2x plus 6. And this bottom one is in fact minus 2x plus 6. Okay? So, what are the integrals? Integrals of these two, so a will be from minus t to some point, which I will find it. Top one minus the bottom one, so the top one is square root of 2x plus 6 minus the bottom one, which is minus 2x plus 6. Plus the other one, the top one is, well, it goes from that point to point, where is it? We haven't found the 2 points, the 2 limits. So let's write the integral, the integrand first. So that is this one, 2x plus 6, minus this one, x minus 1 dx. Let's find the 2 points. If I recall, the y coordinate was 4 and the y coordinate was -2. So the y coordinate of 4 will give me, if y is 4, x minus 1, that gives me x is 5. So this point is 5 here. And if y is -2 and x minus 1, then that gives me x is minus 1. So that's point minus 1. So it goes -3 minus 1, minus 1 to 5. Well, I'm not saying it's hard to find this integral, but just look. Each one of them has root of something. And you need like substitution to find the 2 integrals. So if you can avoid square roots, it might be better. So that's my advice. If you can write the integral in another term and avoid the square root, then do that. Avoid the square root. When we avoided the square root integral of this thing. And you can see that the other one using the y is in fact amazingly simpler than this one. Okay. So let me erase this and do another example. Let's see if I have something interesting here. Yeah, this one is nice and quiet. Well, sometimes you have, so one of them is e to power x, and the other one is x e to power x squared. Well, let's see if we can. So this one is e to power x, this one is x e to power x squared. And goes from 0 to somewhere here. So let's see if we can solve this problem. Is that e to power x squared? So that's in fact one of the problems in the book. Example: find the area of the region enclosed by these two and the y-axis. There's this region. So well, let's see if we can solve with this. So if I let ex equals x e to power x squared, I really don't know how to solve this thing. So Well, let's try. So if I take the ln of both sides, I have ln e to power x equals ln of x e to power x squared. So this one is just simply x. This one is ln x plus ln e to power x squared. That is a times b. Ln of a times b is ln a plus ln b. And this one is simply x. And so x equals, this one is x squared plus ln x. Well, I don't think we can solve this just like that, but let's just assume that this is point A, some point. And maybe next time I will do it. You can use your calculator to find this point using method like say Newton's method or something. But anyway, so let's assume that it is some point that we have found, and so the area will be from 0 to this A that we, which one is on top, e to power x is on top, and the other one is x e to power x squared, dx. Now it's interesting that you can solve both of them. I mean, the integral of e to power x you know, but integral of x squared, I mean x e to power x squared is also, you know how to find that. So let me write this ex dx and minus integral 0a x e to power x squared dx. Well, this one is just e to power x, and this one you can tell that what is the inside function? The inside function is in fact this x squared, right? Inside function is the x squared, that's like the gx, remember? And this is 1/2 g prime x, right? So that one can be solved using integration by substitution. And that is in fact 1/2 e to power x squared. This is 1/2 e to power x squared. And this one is just simply e to power x. And if we can find that point numerically, then we can say something. Well, let me see if there is another way to solve this thing. That doesn't come into my mind immediately. So I guess that's what I wanted to say in finding area between two curves. And the next time I will do volumes. And okay, so see you next.